Well, hello, and I would like to perform a conservation of linear momentum problem, namely for an elastic collision where we have two unknowns to solve for, namely the final velocity of a first object and second object. Let us perform this calculation also only in one dimension. So the problem says a ball of mass 1.00 kilograms moves with a velocity of 2.00 meters per second and collides elastically with a ball that's at rest. That's 2.00 kilograms. What are the final velocities of the two balls, assuming the motion is in one dimension? Okay. Now this problem seems straightforward enough, and the numbers seem relatively easy, which I meant for them to be, but it turns out this problem is actually a pretty long calculation, hence why I have a lot of space here. So let's have a look at the problem. Looks like we have two balls. I'll call them 1 and 2. I'll also refer to them as red and blue. And the initial velocity of mass 1 is 2 meters per second, so it has an initial momentum of 2 kilogram meters per second. And the initial momentum of mass 2 is 0 because its initial velocity is 0. So what we really want to know is what is the final velocity of either of these balls. So what we really want to know is ball 1's final velocity, which I will depict like so. We don't really even know what ball 1's final velocity is in terms of its direction. So let's call it V1 final in the x direction. We don't even know what that ball's final velocity is. And likewise, we want to know ball 2's final velocity. So that's V2 final in the x direction. Now we believe ball 2 will probably be moving to the right because it's collided with and there's a rightward force on it. So in fact, when we talk about that rightward force, we assume that the only two forces in this problem, in this whole system, are internal forces, namely the collision forces, that is the interaction forces, and those forces are Newton's third law forces. And hopefully you recall that Newton's third law forces are equal in size but opposite in direction. So if you consider both balls as the system, they cancel so that the total momentum of the system coming in should equal the total momentum of the system coming out. And there's one other conservation principle we will use since the collision is perfectly elastic. And that's the conservation of energy, and namely the conservation of kinetic energy. So what we will write here is the conservation of linear momentum and the conservation of energy, and we'll write equations for each of those. And in fact, I'd like to perform these separately so that the linear momentum, because there are two masses, it has two terms to start with, and that's equal to two terms that we end up with, and the conservation of kinetic energy has two terms to begin with, and then also two terms that we end up with. Let's write down the linear momentum before and after of mass 1 and the kinetic energy of mass 1 before and after the collision. So that's going to be precisely m1 v1 initial in the x direction, and afterwards that's going to be m1 v1 final in the x direction. And then down here for kinetic energy, that will be 1/2 m1 v1 initial in the x direction squared. And then afterwards, the kinetic energy will be 1/2 m1 v1 final in the x direction squared. Ball 2 we are depicting in green, and as a result, we'll write very similar things, except everything will be for mass 2. So it's going to be mass 2 v2 initial x, and that's the left-hand side here is the total momentum of both masses coming in, and then we need the total momentum of both masses going out. So the second term we need is m2 v2 final in the x direction. And then likewise for the kinetic energy, but there are 1/2s and there are squared terms. So 1/2 m2 v2 initial x squared, and then this is the total kinetic energy inward of both masses, and then outward should be the total momentum of both total kinetic energy of both masses, and that should be 1/2 m2 v2 final in the x direction squared. So let us now look at our plan of attack, so to say. What we can do is we can say there are two simplifications we can make almost right away. And the first is because the initial velocity of mass 2 is 0. So because this term is 0, the initial velocity in the x direction of mass 2, I think this initial momentum will also be 0, and this initial kinetic energy of the second mass will also be 0. Okay? And here for momentum, it's in kilogram meters per second, and here in terms of kinetic energy, it's in joules. Okay, so with that in mind, we can continue to simplify these equations. One more thing, notice the kinetic energy equation has a 1/2 in front of each of the terms. If we multiply the entire equation by the constant factor of 2, then all these 1/2s will indeed cancel. Okay? So let's call this first equation the conservation of momentum equation 1. Let's call this second equation the conservation of kinetic energy equation 2. And let's rewrite those equations in their more simplified form with, and by the way, I'm going to be performing a lot of algebra, so we know that mass 1 is in red, mass 2 is in green, but I'm just going to be switching to the black color because I'm going to be performing a lot of algebra. So the equations end up becoming the following. They end up becoming, let's see, mass 1 v1 initial in the x direction equal to mass 1 v1 final in the x direction plus mass 2 v2 final in the x direction. And then here we have mass 1, that's mass 1, v1 initial in the x direction squared equal to mass 2 v1 final in the x direction squared plus mass 2 v2 final in the x direction squared. Okay, so notice what's going on with these equations. This is essentially the conservation of mv, because that's momentum, and this is essentially the conservation of mv squared for all objects. Notice that this problem has been somewhat simplified because the second mass was initially at rest. In general, it might not be at rest, so the problem might even be a little more difficult. But notice that we have two equations, and we also have two unknowns. So we did not write down the unknowns before, but let's actually write down everything carefully. So what I have here is I have all the knowns written down. I really should have probably written these down at first, but we have mass 1, mass 2, v initial 1 in the x direction. Notice I put a positive on it to emphasize that it's going to the right. And then we have v1 final in the x direction, v2 final in the x direction, question mark. The v2 initial in the x direction was 0. That's what we said here. That's why we're able to eliminate both of these terms. By the way, the entire time we've been assuming the positive x-axis is to the right. So let me go ahead and label that for us. So this should be, this should be our positive x direction to the right. Okay, we've been assuming that. So now we have these two equations, two unknowns, and I don't usually recommend this, but let's go ahead and plug in numbers that we have now. Only because these are not a pair of linear equations, they're actually a pair of a linear equation and a quadratic equation. So it's actually somewhat difficult to solve. Now, the methods that you should be aware of for solving would include graphing and intersecting those two curves. Another method should be basically solving by substitution or elimination. Now, it turns out that I'm going to use the substitution method. So I'm going to use the substitution method. So I'm going to solve for one of the variables and plug into the other equation. Okay? And that should also reveal some insight. Okay, so what I'd like to do is I'd like to copy both of these equations here onto the next board, and then we'll pick up in just a moment. So now I will insert the numbers that are relevant to this problem from the known values that we had on the previous board. So M1 V1 initial will be 1 times 2. I'm not going to worry about the units because we know the units are consistent here. They're in kilogram meters per second. And then we're going to have also 1 times 2 squared, because that's the initial kinetic energy of mass 1. But instead we just eliminated the 1/2. So you might think that's 4 joules. It was actually 2 joules. But again, we multiplied the entire equation through by 2. So let me go ahead and eliminate these knowns. Okay. So let's just rewrite on the right-hand side what these come out to. So 1 times 2, I think, will be 2. And then 1 times 2 squared will be 4. Okay? And then we should also insert for mass 1 and mass 2. So now I've deleted mass 1 and mass 2. And we recall that mass 2 was 2 kilograms, don't forget. And then we recall mass 1 is just 1 kilogram. So we don't really need so much a 1 here, but let's just put a 1 here for good measure. Okay? And let's take a look at these equations. Notice that the first equation is a linear equation, and I think V1 final x should probably be the easiest to solve for. And notice that the second equation is a quadratic equation. We would not like to introduce a square root and have the uncertainty of the plus and minus if possible. So let's solve for V1x final. So let's write this down. Solve, and let me label the equations again. This is equation 1 and equation 2. So let's summarize by saying solve equation 1 for V1 final in the x direction, and then substitute into equation 2 to find V2 final x. Okay, so this is what we're going to do. So let's in fact do that. So that means V1 final x, the final velocity of mass 1 in the x direction should be 2 minus 2 V2 final x. And again, you could call that equation 3, but the whole idea is that we're going to substitute equation 3 like so. So the double underlines are going to tell us what we're going to substitute. We're going to substitute that into equation 2 for V1 final x. So notice that we're going to have to square this term. Okay, so we find that we'll have this term got substituted in and it's squared. So it's 2 minus 2 V2 final in the x direction squared. Whoops. The entire thing is squared, that is, plus 2 times V2 final in the x direction squared equals 4. Now I want to remind you of something. So here is what I believe to be an important reminder. So recall from your algebra courses that this is a binomial subtraction squared. So that's like a minus b quantity squared. And if you recall, that's a squared minus 2ab plus b squared. So we will use this property, in fact, down here. So what do we get? We get 4 minus, and remember it's 2 times the multiplication of these two terms. So 2 times 2, negative 2 is negative 4, doubled is negative 8, v2 final x, and then we're going to have plus 4 v2 final x squared plus 2v2 final x squared equals 4. Okay, let's see how we can clean this algebra up. So now I'm back to the purple color in order to clean the algebra up. Notice that these two terms are like terms, so these can be combined. So we'll do that in just a moment. And look at this. This positive 4 and this positive 4 on both sides, somewhat serendipitously in this problem, these are going to cancel. So they're constant terms, and you can just subtract them from both sides. So let's see what we get. Okay, so writing the quadratic term first, we have 6v2 final in the x direction squared minus 8v2 final in the x direction equals 0. Now notice we have a quadratic equation with no constant term. So we don't necessarily have to use the quadratic formula. We actually could use factoring if you like. So we should factor the greatest common factor. Factor the GCF, right? The greatest common factor. So I think 2 and v2 final x are both greatest common factor. So that's 2 times v2 final x times the quantity of 3 v2 final x minus 4 equals 0. Okay, so now let's take a close look at this. Recall, v2 final x was the final velocity of mass 2 in the x direction. So we want to think about these solutions. What I've done is I've switched to green to remind you this is the final velocity of mass 2. So in fact, let's look at the previous diagram. Notice we expected mass 2 to move to the right. Notice also if we allow this first solution to possibly be 0. So what if this solution is equal to 0 by the factoring? Well, then v2 final x, could that possibly equal to 0? We say physically no. That's not a valid solution, because if there's a rightward force on it, there's no way it stops. So we reject this solution physically. But now that means this is the solution. So 3 times v2 final x minus 4 equals 0. So that means this entire term equals 0. So that means v2 final in the x direction is equal to, add the 4 over and divide by 3. So it's going to be positive 4 over 3 meters per second. That's going to be the final x velocity of the second mass. So positive 4/3. And if you write that as a decimal, which I think we'll show with a little simulation here in just a second, that's equal to 1.3 repeating meters per second. Okay, so 1 1/3. Now the question is, what's going to be the final velocity of mass 1? Well, mass 1 is actually given by equation 3. So what I've written here is return to equation 3 to find v1 final in the x direction. That's the final velocity of mass 1. So let's write v1 final in the x direction equals 2 minus 2 times the final velocity that was in the x direction of mass 2, so that's 4/3 meter per second. And that's a positive number. So this is negative 8/3, and then 2 is the same thing, I think, as 6/3. So we have 6/3 minus 8/3. So this should exactly equal to negative 2/3 meter per second. So this should be the final velocity of mass 1 in the x direction. Now let's see if that seems to be physical. Let's go back to the original diagram. So mass 1 is a smaller mass than mass 2. Mass 2 has more inertia than mass 1 does. Mass 2 comes in with a positive velocity, positive momentum, but because it's elastic, we say it bounces back, that this is negative 2/3 of a meter per second. And we also say that this right here is actually a pretty large velocity. It's positive 4/3 meter per second. And this seems reasonable because there's a rightward force on mass 2. There's a leftward force on mass 1. Mass 1 is a smaller inertia than mass 2, so it does bounce back. Now notice, we believe we have the correct answer. Now one more thing, you may say, do we have to go through all this work every single time? I mean, for example, what if the numbers were more difficult than just 1s and 2s? Secondly, what if the second mass was not at rest? That also makes the problem more difficult. And then third, what if the quadratic does not just factor? What if you have to use the quadratic formula or something? And what if you really have to think about which are the correct solutions? Well, in order to do that, we need to have a more sophisticated, a more thorough recipe for the final velocities of two masses when they collide in one dimension elastically, namely the conservation of momentum and the conservation of kinetic energy. So what I have on the next board is what is often called the recipe for when two objects collide with one another elastically and they have different masses and different initial velocities. So notice that the final velocity of mass 1, that is the final velocity of mass 1, what we're calling in red here, has to do with its own initial velocity, but then also the difference between that mass and the second mass divided by the sum of the masses, but then it also has to do with the sum of the masses, but then also mass 2 seems to have more influence. Notice that object 2's final velocity does involve the initial velocity of mass 1, and it certainly involves mass 1 more, but it also involves the difference between those two masses. So notice the full-on solution, if we had solved that pair of equations, the conservation of linear momentum and the conservation of the kinetic energy, if we had solved that in its full-blown form, notice that what we would have found this for the final general equations, that something about the difference in the masses and something about the initial velocities give the recipe for the final velocity of mass 1 and mass 2. Now let me just say, these equations are definitely not obvious. I would suggest if you're trying to work this out on a homework or an exam, you have these equations written down somewhere. I certainly don't have them memorized. But what I will say is that it certainly makes the calculation much easier. Okay? So in the last problem, if we had plugged in 1 and 2 for mass 1 and mass 2, and we had plugged in V initial as 1 meter per second, the second mass was at rest, then these two terms would have gone away. So we'd have had 1 minus 2 over 1 plus 2. So that's negative 1 over 3. Actually, I think that the initial velocity was 2 meters per second for mass 1. So we'd have got negative 2/3. So that was the correct answer for the final velocity of mass 1. And then for mass 2, we'd have plugged in 2 times 1 over 1 plus 2 times 2. So that's 2 times 2 upstairs divided by, again, 3. So that would have been positive 4/3. And that's exactly what we expect. Notice it gives us the answer much, much quicker without having to go through all that mathematics. So in fact, let me show another example that's a little more complicated. Imagine mass 1 is moving at 5 meters per second, and it has an initial, or sorry, it has a mass. So mass 1 is 0.7 kilograms. And imagine mass 2 is a much larger mass, namely 3 kilograms. What are going to be their final velocities? Well, at least since mass 2 is at rest, this term equals 0, and this term equals 0 in this problem. Okay? So we can just solve. So we can say V1 final is equal to, and that's going to be 0.7 kilograms minus 3.00 kilograms divided by the sum of the masses. So that's going to be 0.7 kilograms plus 3.00 kilograms. That whole thing times the initial velocity of mass 1, that's 5 meters per second. And then we can do V2 final is equal to the same sort of thing, but it's 2 times mass 1, so it's 2 times 0.7 kilograms all over 0.7 kilograms plus 3.00 kilograms times 5 meters per second. Okay, so V1 final and V2 final. So let's calculate these values on the scientific calculator. So I'll use alpha F1 to get the menu that gives us n over d, which is numerator over denominator. And that will give me a nice fraction stack here. And I will type 0.7 minus 3. We don't need to include all the significant digits in the actual calculator. And then divided by 0.7 plus 3. So that's the difference in the masses divided by the sum of the masses multiplied by the initial velocity of 5. Okay, that's going to be our first answer. Then I'll use second entry, or I could use the up button to enter this because the next expression is very, very similar. But what I want to do is I only want to change this minus 3 and get rid of that. I'll keep the 0.7, and then I'll do second insert mode 2 times 0.7. And then hopefully this is correct. Let's do enter. And then we have 1.89 meters per second. So let us write these values down. We should have negative 3.11 meters per second for the final velocity of mass 1. That's the red ball. And then we should have approximately, let's see, 1.89 meters per second. That's a positive for the velocity of the second ball. All right. Notice I boxed each of the final velocities in red and blue, respectively, for mass 1 and mass 2, because that's how we've depicted them in these problems. So let's now see if we can verify that those collisions that we calculated for before are indeed the case. So let's imagine ball 1 is moving at 2 meters per second to the right in the positive x direction, and that ball 2 is at rest. That's its initial velocity is 0 meters per second. And let's also assume that its momentum is 0 because it's at rest. Also, let's assume that ball 1 is 1 kilogram and ball 2 is 2 kilograms. Let's also take a look at the velocity of these objects before and after the collision. The collision will be entirely one-dimensional. It'll be perfectly elastic, and it will be without friction or air resistance or anything like that. So let's see if we can verify that negative 2/3 and that positive 4/3. So that is indeed what we see. Now, by the way, the negative 2/3 and the positive 4/3, these are just rounded, but they should be exactly negative 2/3 and positive 4/3. Let's see if we can also verify this using momentum. Okay, so let's put the momentum diagram here. Okay, so ball 1, the red one, starts with 2 kilogram meters per second. Ball 2 starts with 0 kilogram meters per second momentum. So ball 1 has the total initial momentum. Let's play. And notice afterwards, ball 2 has quite a bit of momentum because it's a larger mass. Ball 1 has negative momentum, but the same total momentum is still preserved. Okay? And even if we look at the kinetic energy and not the momentum, we should see that the kinetic energy is indeed conserved. There's no change. Finally, let's also see if we could verify the second collision that we had. Namely, a 0.7 kilogram mass hits a 3.0 kilogram mass. Notice that this was a harder problem to calculate because the masses aren't quite so nice. This velocity is much larger, and notice the momentum is 3.5 kilogram meters per second coming into the calculation here. But let's see if we can get this experiment to work out. So 3, 2, 1, go. So notice that here we have negative 3.11 and 1.89 meters per second for the final velocities. So this is what we saw when we calculated the final velocities using the recipe. And this is, again, what we expect. There are more difficult numbers to calculate, especially using the quadratic formula or intersection of curves or anything like that. Let's see if we can verify this using momentum. So let's take off the velocity, show the momentum and the momenta diagram. So the initial momentum is only that of mass 1. It comes in. Notice that at the end, mass 2 has a large momentum because it's a larger mass. And then mass 1 rebounds. So moves to the left, has a negative momentum, but again, the sum of them equals the same total momentum we had before. And then finally, the kinetic energy should remain the same. So that looks like this. And notice the kinetic energy does not change at all. And also just one more proof of how difficult solving these equations can be if we don't have those more complicated, sophisticated equations that I showed for the second problem. Notice that if we don't use the substitution method, we either have to use the elimination method, which can be difficult, or we have to use a graphing program. So notice what I have here is I have the equation y equals 2 minus 2x. Now you may recall y equals 2 minus 2x corresponds to the final velocity 1 of mass 1 in the x direction equals 2 minus 2, and that's the final velocity of mass 2 in the x direction. So y is mass 1, and then x is mass 2. So that's exactly what we have here. We have mass 1 on the vertical axis and mass 2 on the horizontal axis. And notice it's exactly a linear function. Okay, that's what we kind of expected. Now how about the second curve? So the first curve is in orange, the second curve is in blue. Now the blue curve, the second curve, is going to be the shape of an ellipse. How do we get that? Well, if we look at this second equation, that's like our y squared plus 2x squared equals 4. If we divide the equation by 4, we'll have exactly what I have shown here. We'll have y squared over 4 plus x squared over 2 equals 1. Hopefully you recall this to be the equation of an ellipse. This has a semi-major axis along the y-axis of 2 and a semi-minor axis of square root of 2, which is about 1.41 or so, right there, along the horizontal axis. So notice we have this point along the major axis, and then this point and this point along the minor axis. This is not a circle. Notice where that linear line intersects this conic section is going to be precisely the solutions that we're looking for. So notice that this solution was the one we threw out, that mass 1 would keep moving at 2 meters per second, but then mass 2 would completely stop, and mass 2 wouldn't move at all, and then mass 1 would completely would move at 2 meters per second. But this is the correct solution. Notice the correct solution is when y is negative 2/3, then mass 1 rebounds at negative 2/3, and then when mass 2 moves, it moves 4/3 of a meter per second to the right. By the way, I also want you to note one other kind of interesting thing, and that is, if you take the absolute value of these two values, positive 4/3 and negative 2/3, notice that they equal 6/3. That's the same thing as 2 meters per second. And notice that's because that's the initial velocity. Now, by the way, that's because one of the masses is also at rest. And it turns out these problems can be solved in a different method using relative velocities, which I haven't shown in the lecture slides yet, but I believe I'll show that as a supplemental lecture as well. Okay, just wanted to show you several methods to solve these problems. So, after that verification, I want to thank you very much for watching this video. If you like this content, please smash that like button, and please share this video with those that you know to grow the channel. I want to thank everyone that supports this channel, and please subscribe, and I will see you in the next video.